Hi guys, I'm sure all of you are doing well. So through this video series, um, I have actually thought of to share my ideas, share my views, and welcome all of your opinions about the topics that I will discuss in subsequent time periods. So at a high level, all my video series will be based upon the supply chain concepts and different modules or different logics or different functions that we use in a day-to-day supply chain planning. Okay, so today I I will discuss about one of the very important forecasting model that is called as simple exponential smoothing. So in my entire video today, I will focus on this simple exponential smoothing function and how we can implement it using Microsoft Excel first. So I'm sure all of you, some of you must have been already heard about it. What is simple exponential smoothing? I will not go much about theories behind it. Probably if needed sometime later, I will discuss. But today in this video, I will focus mostly on the statistical data analysis and of the simple exponential smoothing function using Microsoft Excel. So once we understand the logic behind the simple exponential smoothing function, the same logic we can extend it to implement in different languages called R or Python. So without wasting much time, let me open the Excel and share my screen. Okay, so I'm sure all of you are able to see my screen. So here, I have taken one sample data set here. So this data set says about the different inflation rates we have. Let's say this is in percentages, okay? Different percentage of inflation rates that we have captured in the previous quarters. So as you can see here, the column A here, I have taken the time quarters. It starts with September 2013 and all the way till September 2021, we have the data that is called your inflation rate percentages. So what is the main goal of this exercise? As we are standing here in the future, let's say the upcoming quarter is December 21. So we are here to forecast what could be the inflation rate in the coming quarter or in upcoming quarters also. So first of all, we will try to forecast the value for one quarter, 1 point forecast in the future horizon. Okay. So let us see how we can do this using simple exponential smoothing function. So the simple exponential smoothing function is mostly applied whenever the data has a level component in it. So what is the level component? Maybe in a separate session, I will explain what are the different seasonal components we like, trend component, seasonal component, level component we have in the entire historical data, in a time series data. Okay. So today let us assume we already know that what is a level component in a time series data, and we are here to implement the simple exponential smoothing function. Now let us see in Microsoft Excel how simplified way we can use it. Now, before implementing any time series models, we will have to plot the time series historical data. It's always a good idea to plot so that the different patterns of the data, different nature of the data, it's get visible automatically when we plot in a graph. So to start with, let me select the entire horizon. I'll click on insert and I will just try to draw a line chart. It's very simple, right? So as you can see here, the data, yes. So as you can see the plot here, the data mostly has a level component. Are you able to visualize the level component? If not, let me try to explain you. Let me select the trend line. Okay. And let me go to formatting the trend line. I will have the red color in it. Okay. Now, as you can see here, mostly the data revolves around this particular trend line, right? Now, this trend line, as you can see here, it is mostly a horizontal line, which is very parallel to the horizontal line, okay? So that means definitely this data has a level component in it. Now, let us try to implement the simple exponential smoothing function, okay? So before implementing the SES function, one thing we have to note, we have to understand that what is the formula behind it. In the second sheet I have captured here, I have actually mentioned the simple exponential smoothing function here. And alpha, the smoothing parameter, we call it as alpha. It's nothing but the smoothing parameter. Okay. As you can see in the formula, the alpha, the smoothing parameter, the weight of the alpha is directly applied to the previous observation. So here what I have, this yt minus 1, that is my observation. Y is my observation. And F stands for the forecast. Okay. Now let us try to implement the same formula in Microsoft Excel. Let me take another column here called forecast F, and I will take a value called alpha here. Okay. And that means the value of whatever alpha, I will put it over here. I will try to relate the formula of this forecast using this alpha value. All right. Now, one thing we have to assume here, that before implementing the SES function, we need one seed value of the forecast always. So what is the seed value? The seed value is something that, to start with, the forecast value is always equal to the demand observed in the previous. Let's say this forecast is equal to 0.6. So here I will have this as an assumption here. Okay, so that means this is my seed value. So seed is assumed to be 100% accurate to the the demand. So that's why for September 13, as this is my starting time bucket, so here what I have done is I have simply equated the forecast value for this inflation rate is exactly equal to the demand, 0.6. Okay. Now, in the second, for the time buckets, I will forecast using this simple exponential smoothing. Now, how I can do it? What is the formula what we have spoken? It's like alpha times the previous observation, right? Plus 1 minus alpha times the previous forecast. So this is my formula that I just implemented using simple exponential smoothing in Excel. Right? Now, this alpha value is constant because for all the future weeks, I will have to use the same alpha value. So what I will do here, I will just have these dollar signs so that the reference doesn't change. Okay, now I'm done. After that, I'll simply extend it. You can see it. We have all the 0.6 came up. But remember, we have not assigned any value of alpha here. So alpha is the smoothing constant, or what we can call it as a smoothing parameter. The, the, the range of this alpha, 0 less than equal to 0 to 1. The value of alpha always is maintained between 0 to 1. That is one of the constraints we have this in this particular simple exponential smoothing function. Okay, so now let us select, let me take the value of alpha to be, let's say, 0.2. Okay, now if you see in 0.2 how the values are getting, the different forecast values I'm getting, right? Now what I will do here in my graph, what I have taken, I have not considered the column C, right? So what I will do, I will extend it to consider the column C as well. Give me a second. Select data, chart range, and that's all. Okay, so as you can see here, let me expand it a bit more. As you can see here, my forecast value, this is my forecast, okay, and these are my observations, right? Now as you can see here, the different forecast and these are the different observations, right? Now we have plotted in a graph. Now we have to see which value of alpha is actually giving the most accurate forecast. Now whenever it comes to accuracy of a forecast, that means there is an error component that lies behind every forecast. That's the reason probably we say forecasts are always wrong. It's just that we can say how accurate is the forecast is, but we can never say that a forecast is right? It's always wrong. So when it comes to different error metrics in a forecast modeling, there are a lot of different error metrics we have, but to focus our discussion, to limit our discussion, we will focus on, let's say, mean absolute error and mean square error. Okay, let me show you how we can do it in Excel. Let's say this is an error. So this error, the error formula is simply the subtraction between the demand and the forecast. So this is my observation and this is what I forecasted, right? Simply I will just till period 34. Yeah. So this is my error component. Now my goal is to calculate, as I said, we will focus on calculation of the mean square error. Okay, that means we will have to calculate the squared errors first in another formula. So what is the squared error meaning? It's simply the square of the errors, right? So we got it. Now if we say MSE, this is called mean square error. This is nothing but the average of all my squared errors. Simple. Okay, so this is my MSE. Now if I will change this alpha value, let's say 0.6, you will see the forecast is always if you observe in the graph, the forecasts are getting changed. And similarly, the error is also changing. Okay. Now, to reflect in a better sense, let us take a 2 point or 3.4 error. Okay. And similarly, yeah. All right. Now, our goal is to calculate the optimal value of alpha. So when I say optimal value of alpha, that means the value of alpha which gives the lowest possible mean square error for the given data set. Because we don't know what is the alpha that we will have to consider while we implement a model. So that is something that we want the system to recommend us. Now let us see how we can do it in Excel. To do this in Excel, we will have to go to the Data tab, and we will have to use one Excel add-in function, Excel add-in, that is called the solver. So in case you do not find the solver add-in in your Microsoft Excel, you will have to follow this path. Go to File, go to Options, then go to Add-ins, and here click on Go to see the different Excel add-ins, and make sure you just click the solver add-in. Okay. So once you do this, you will have an access to this solver add-in feature. Okay. Now let us see how we can get the optimal value of alpha using Microsoft Excel solver for simple exponential smoothing. Now click on solver. Now what you have to do, our objective. So what is our objective? If you will see, I just told that the objective, our objective is always to minimize the errors. So in this example, what we just discussed, the mean square error, let me equal to this mean square error. That means this is my objective function. Okay. Now, what is my goal? As I said, I want to minimize. So I will click on minimize. So minimize this objective function. Minimize the mean square error. By changing what will I have to change? I have to change the value of alpha. So by changing the value of alpha, I want to minimize the mean square error for this given time series data. So that's all I have formulated here in Microsoft Excel. Now, one thing we have to note that there are a couple of constraints, right? So what we have to do, we'll go to add, and we will select this alpha. As I said, the range of alpha should be lying between 0 and 1. That means it is less than equal to 1. Another constraint is it's greater than equal to 0. I will click OK. Okay. So now I have already formulated the constraints. I have formulated the objective function and the variable, right? Now I will click on solve. Now, once I click on solve, you will see the keep solver solution restore original values. So I will click on keep solver solution because I want to see what are the different, what is that optimal value that the solver has given me. So I will click on keep solver solution and I will click on OK. Okay. Now what I will do is I will increase the decimal places to maybe 2 places of decimal or 3 places also you can take. That means for this given data series, for the value of alpha equals to 0.061, I'm getting the mean square error of 0.101. And as for the solver, this is the minimal mean square error. That means This is my optimal alpha. So this is how we have implemented the simple exponential smoothing function to the time series data. Now, if you will see the different forecast that we will have to get now for the December 21 for the upcoming quarter, now 0.5. In case you want to see the forecast value to 2 decimal places, then you can have kind of this. Okay. Similarly, let's say we want more forecast numbers to be there for the upcoming quarters. That means, let's say March 22 also we want to forecast. That means we will simply extend it. And if you will see in the data, if you will see the forecast function goes like this. So as you can see here, this was my trend line, what we have plotted here, right? This is the trend line. And from the trend line, we can see the data resembles a level component within it. And the forecast that we are getting is closely in association, is closely related to this trend line, right? That means this is definitely one of the good forecasting models, simple exponential smoothing, that we can think of applying to the time series data that has a level component in it. I think that's all for today. In case you got any questions, you got any views about this, please feel free to comment, and we will learn together from each of our discussions. So till then, next time in my next video, I will come up with another forecasting models, and we will see how these forecasting models we can implement using R and Python also. Okay, so till then, take care.